Okay, very good. All right, so let's take a look at how to write a rate law. So if you're looking at problems like number 3 on the bottom, or if you're looking on the back at problems like 4, 5, and 6, and I should say that questions 4, 5, and 6, there will definitely be one like that, definitely, because that's like the big style of problem that you see. But let's take a look at number 3. First of all, every time you have a chemical reaction, you can write a rate law for it. And the generic rate law is always the same. So if I've got NO plus H2.
Wait, can we write the generic rate law?
Well, we're going to. Just hang on. Give me one thing at a time.
Okay.
So we'll do N2 and H2O. And I have to put a 2 there, and a 2 there, and a 2 there to balance it. Okay. Whenever you are asked, if you're given an equation, and you're asked to write the generic rate law, which will probably be a question, it's always the same. It's the rate is equal to some rate constant K times the concentration of the first reactant raised to some power times the concentration of the second reactant raised to some different power. Now these powers, these exponents, have nothing to do with the coefficients when we do rate law construction. You have to do experiments by changing concentration. Now, okay. Plus, this is all going to be on video too, so if you need to sit down and watch it, maybe it'll be helpful if you just listen today and then go back and watch the video and take your notes. Because I think what happens is you get distracted trying to write it, and then things, they kind of pass over you. So just sit back, relax, and you can go watch the video many times as you need to.
Okay.
Now these M and N all are called orders of reaction with respect to the reactants. Okay? So the values can be 0, 1, 2. We very seldom see anything that's larger than 2. So anyway, the total overall order is M plus N. So if this is first and that's first, the overall order is second. Now, you can have a 0 order. That means that changing concentration doesn't have any effect. And if I have a 0 for one of these, I can just remove it from the rate law, because anything raised to the 0 power is just 1, except 0.
So it doesn't, if it has a 0 power, then it doesn't change at all?
Yes, if I'm changing the concentration of something and it has no effect on the rate, that's called 0 order reaction. Okay. All right, so now they show us the actual rate law. There's a 2 up here, and there's nothing up there, so it's a 1, right? So we say this reaction is second order with respect to nitrogen monoxide, and this reaction is first order with respect to hydrogen, and it's third order overall.
Because it just has a 1 up there.
Right. And you could write, it's not wrong if you put the 1 up there. If you need that to kind of help you, help work through the problem. I don't care about that. Because you're correct. Now, what about the rate constant? Saying, what is the unit on rate constant? And let me show you how to get that. Rate constants, unlike equilibrium constants, we need a unit on there. So rate is always going to be molarity per unit time. Could be molarity per second, it's changing, molarity per minute. So molarity per time. Now, these brackets mean molarity. So my K here, I have to have a K that ends up giving me these units. because I have a molarity squared here and a molarity there. Right? So on this side, I have molarity cubed, so I want to get rid of the molarity cubed. So I multiply both sides by 1 over molarity cubed. That'll get rid of those units. And then what I have here, that molarity cancels with 2 of those, or with 1 of those rather, and I have 1 over second times molarity squared. And probably what you want to do there is write it like this. S to the minus 1, m to the minus 2.
If we write it like that before, though, is that right? And that's
Yeah,
okay?
they're both correct. Yeah,
Okay.
both of them are correct. It just looks a lot better. Like if you have a rate constant that might be 1.7, or 714 second to the minus 1, molarity to the minus 2. It just looks a little tidier than having that. Okay.
Okay.
So, but both ways are correct.
Yeah, the first way, I mean, that on a test, I'll be more. That'll make more.
Yeah, these are identical. Wonderful. Now.
I also can't see it because of the.
Oh, okay. Yeah.
But that's okay.
Yeah, like I said, 1 over second molarity squared is equal to second to the minus 1, molarity to the minus 2.
Thanks.
Okay. Now, let's go ahead and look at these types of problems on the back. Okay.
I can sit here and learn chemistry.
Yeah.
Yeah. Okay.
Anna's getting a one-on-one session.
Oh, nice. Okay.
So
Much needed.
let's take a look at question number 5 on the back, and I want you to try question 6 on your own. Okay? Because if I do them all, it's not going to be very helpful. All right. What's that?
Very.
Not in the learning process.
Yeah. It
So-
actually helped me a lot to watch and do it.
Well, you can watch me do number 5, and then I'll shut the recording off, and you can do number 6 and see what you come up with.
Okay.
So I've got 2ClO2 plus 2OH minus, and we get ClO2 minus plus ClO3 minus plus H2O. And then ClCl, 2Cl, 4 oxygens. Oh, wait. 4, 5, 6 oxygens. 3, 6 oxygens. We're good. We're balanced. Okay. Now, write the generic rate law for this reaction. It's always the same. Generic rate law, K, lowercase, first reactant. We don't know the exponent. We have to look for that experimentally. Remember that you can't put a 2 there. That's equilibrium. This is kinetics. And over here we put OH minus to some other exponent. And these values can be 0, 1, or 2. So, in the first question, they say, what is the order of the reaction with respect to that? Chlorine dioxide. So you have to look for 2 experiments where this is held constant and we're changing that. Because if we change that and don't change that, we can say, okay, I can get the effect on the rate by changing this one. So I look here, and you might say, well, experiments 1 and 2, I have 0.05 and 0.051. That's close enough to being the same that it's not going to have an effect. Okay. So, I mean, this is like real data. It's not like just it's made up, but it's made up to look like real data that you'd use. So in those 2, now look, experiments 1 and 2, I want you to look at this backwards. Take experiment 2 and then compare it to experiment 1. I'm doubling the concentration between those 2. So what you do, you know what? This could help you. You take the larger value and divide by the smaller value. 0.05 divided by 0.025. That's equal to what? 2. Now, do the same thing with the rates. Take the larger rate, 0.288, divided by 0. That should be a 0 there. 0.00733. And now go ahead and divide that. And I suspect you're going to see a number very close to 4.
Do you want me to do it?
Yeah.
Yeah, you're really close to 4.
That's pretty darn close to 4, isn't it? So, Anna, if I double that concentration and that goes up by a factor of 4, what's my exponent?
Doubles. Then the order would be
Yes. Good. Yeah. Now let's take a look at runs 2 and 3. In runs 2 and 3, we're holding that constant and we're changing the concentration of that. As a matter of fact, we're going from a concentration of 0.051 up to 0.152. So what is that? That's roughly a factor of what?
Wait, what are those numbers from?
The problem. They're the concentration.
Concentration of OH.
Yes. Divide the bigger number by the smaller number. You can do that in your head. Now do the same thing with the rates. Take the bigger number, divide it by the smaller number.
But I already did that, didn't I?
You did it for the other reactant. You have to do it for both reactants.
Yeah, because you need the exponent.
Yeah. And I bet if you divide 0.021 by 0.007, you're going to get?
Wait, where are you at? In the experiment?
Yeah. Mm-hmm.
021?
Yep.
Oh, what? 0218.
And divide that by 0.00733.
Okay.
You get 3.
Okay.
So, if I triple the concentration and my rate triples, what's my exponent going to be?
That'll be 1.
1, yeah.
Because if it's less than 4, then...
Well, it means that for every 1 step in concentration, I get 1 step up in rate. So if I change concentration by 3 and the rate goes up by 3, first order. So the overall...
Oh, because they both changed by 3.
Mm-hmm.
So
Yeah.
it's just first order. So that one, if it changed by...
If that changed by 2...
Or if that changed by 4 and that changed by 4, then it would be 1.
Yeah. The only time you have to worry about squaring that quantity is if you double 1, or if you triple 1 and the rate goes up by a factor of 9, that 3 squared is 9. So whatever, like if you double the concentration and the rate goes up by 4, you have to square that doubling of the concentration. You know what I mean?
Got it before, but...
Well, think of it this way. I mean, if I have a concentration of 2, and the rate goes up by a factor of 4, I double my concentration. Well, what do I have to do to that 2 to make the rate go up by a factor of 4? Square it, right? If I triple the concentration and the rate goes up by a factor of 9, what do I have to do to that to get 9? Square it. So if the rate increases by the square of the change of concentration, it's second order. All right.
So if it doubles, it's second order.
No, if it doubles and you double concentration, it's first order. Remember, we're looking at an exponential relationship. All right, I'm going to shut this off, and I want you to try number 6.